What up, guys? So it's Polynomials introduction. Just basically going back over the lesson that some students have already seen, some students haven't seen. I'm going to do my best to go through this packet and give examples of every single thing that's going through with this version of the lesson. If you need a version of this packet, please check Canvas. It should be posted up there. Anyways, so what are polynomial their key features? It's kind of our essential question, and your objective here is I can identify those polynomials. Specifically, I can identify their end behavior and zeros with their multiplicities by factoring first. So a lot of different words here. We got to learn what polynomial means, what end behavior means, what zeros are, multiplicities, all these different things. Got to learn. Okay, so first of all, polynomial of the expression an times xn blah 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 looks like this. This is a fancy way of saying questions of stuff that you've seen before. Ignore the letter A there. Stuff that is looking like this. Maybe f of x is going to be 4x squared minus 3x plus 2. Saw a question like this, I'm sure, in your Algebra 2, Algebra 1 years, where we call this one a quadratic equation or a parabola. Instead, now we are going to be calling this a polynomial of degree 2. And we call it a polynomial of degree 2 for a very simple reason. It's because this is the largest exponent in the question. So the largest exponent is going to get us our degree. So a couple things about this. So you've seen these polynomials before in your work. However, how do we tell the difference between what is a polynomial and what is not a polynomial? So the biggest rules are a couple of them over here. I've all written them down over here. All the a's, which I've written in front, can be any real number, including zeros, fractions, square roots, etc. They can be anything they want. But all the exponents must be whole numbers. No negative exponents, no fractions, decimals, square roots, etc. So examples of yes polynomials. I'm going to ignore the f of x, but all these should have basically an f of x in front of them. Answers of yes polynomials might be the square root of 2 multiplied by x to the 4th power minus 3x minus 8.27 plus pi x squared. That's a yes. Anything that has x's with integer values that are 0 or bigger, so 0, 1, 2, 3, etc., is okay. Remember that this guy right here has an invisible 1 that's right there. And right here, there's actually an invisible x to the power of 0. But remember, x to the power of 0 is just equal to 1, so you don't even write it. So every single term does have an x attached to it with an exponent. In this case, this would be a 4th degree polynomial, by the way, so because of that largest 1 there. If I wanted to say a no, however, there's a very, very close difference. If I instead had the square root of 2x plus 3, now this is a no because the square root goes over the x. If the square root is on top of the x, not allowed anymore, no good. Other things of no's, you can't have any version. This is actually a fractional exponent. You can't have any fractional exponent, so x to the 1/3 is a no. If I were to have like a 1 over x, remember that's the same thing as x to the -1. That's a negative exponent. That's a no-go. So a lot of examples, actually infinite number of examples of both of these. But the main point that I'm trying to get across here is that the no's have square roots over the x's, and it's most important to look for these integer values on the x. And the numbers in front do not matter. Numbers in front can be anything whatsoever. So when you're doing these questions here at the bottom that I made in this packet, you're basically just answering a couple of things. So is it a polynomial? If it is a polynomial, find the leading term and its degree, then write in standard form. So the leading term, by the way, is the one that has its degree. It's that largest exponent. So let's just check out this problem number 3 here. In this question right here, there is my largest exponent. So this entire thing we would call our leading term. I like to abbreviate this LT. LT is -1/2 x to the 4th. This is going to be a very important idea later. We would write this as a degree. The degree is going to be 4 because it is that largest exponent. And finally, to write it in the quote-unquote correct form would be to write the largest exponent first, So it would be g of x is negative 1/2 x to the fourth. Then you go down in exponent size, x cubed plus 8. So just make sure you're writing in the correct order for the quote-unquote standard form. Something students get confused about. They see a fraction and they say, hey, the fraction means it's not a polynomial. It is still a polynomial. It's still a yes. The fraction can be there. It cannot be in the exponent. So the exponent can't be a fraction. Be careful. Number 2, we just talked about, this is a big fat no, not allowed, because in the event that you have a square root over the x, always no. However, this one is a yes, because the square root is on the 2, but not on the x. So there is your key concept. The leading term here is actually the only term in this one. There's just the 2x there. And the degree, remember there's an invisible 1. So there's that invisible 1 there. That's why our degree is 1. And it's already in standard form, so I'm not going to rewrite it. I think that's enough examples of this type, so I'm just going to go on to the next idea, the next big one we want to talk about, the root or zero or solution. So the root or zero solution is going to be a very common thing throughout all of pre-calculus, really all of Algebra 2. Should have been a good one to know, but in case we forgot, root or zero or solution, all these words mean the same thing. It is any value of x which makes a polynomial, or any other function, equal to 0. So it means that when you plug it in, do you get 0? So here's my function example. By the way, this is a third degree polynomial. Here we go. The leading term is x cubed. If x is equal to 3, I'm going to replace this guy with a 3, that guy with a 3, that guy with a 3, and that guy with a 3. If I replace every single one of those with a 3, and it being 27, 18, 27, subtract, I get 0. And therefore, we would say, yes, x equals 3 is a 0. Over here, if I plugged in 0, I would get 0 cubed minus 2 is 0. But by the way, just a cute little note here on these polynomials, because all of these would be 0 right away. We can actually just jump and know that 18 is the answer right away. Anyways, no, x equals 0 is not a 0. This is confusing to hear. 0 is not a 0. What? X equals 0 is not a 0 because if I plug in 0, I don't end up at 0. But 3 is a 0 because if I plug in 3, I do get 0. You could try these next ones on your own. I'll let you guys try it on your own time. But the idea is if I plug in 1, I'll get a number that's not 0. So the answer ends up being no. But if I plug in 2, I get 0. So the answer ends up being yes. But it's the same idea. You're looking for what number are you plugging in. Try it on your own is my recommendation. The next problem here, a factor. So a factor of a polynomial depends on the 0. So if x equals k is a 0 of the polynomial, x minus k is a factor of the polynomial. So you can't even define a factor unless you've defined a 0 first. So if you notice, if x is equal to positive k is a 0, then negative k is a factor. The idea is, remember, if I make x equal to k, k minus k is 0. We also have the same idea here. If x equals k over ax minus k is a factor. And every single exponent of a factor is called its multiplicity. So the multiplicity is the exponent that is on the factor. There are invisible ones on all these guys here. And also, the sum of all multiplicities is equivalent to the degree of the polynomial. Let's see some example problems that use this idea. So it says, it wants us on all these questions to, based upon the above definition, create a polynomial in factored form with the following properties. So we're trying to make a polynomial in factored form that has these properties. Zeros of x equal to 1, 2, and negative 4. So the very first thing I'm going to write, put an f of x up there. I'm going to write x minus 1 times x minus 2 times x plus 4. The reasoning why I did that is that if x is equal to 1, minus 1 is the factor. If x is equal to 2, minus 2 is the factor. If x is equal to negative 4, positive 4 is the factor. Concept of the definition. If I plugged in 1, I would get 1 minus 1. That's 0. If I plugged in 2, I would get 2 minus 2. That's 0. If I get negative 4, plug it in, I get 0. Concept is, plug these in, you get 0. The opposite version is the factor. All odd multiplicities. What that means is every single one of these exponents must be odd. So they're already all odd. 1 is an odd number. 1, 1, 1. Great. The degree is 5. Remember, the addition of all the multiplicities has a degree total. So 1 plus 1 plus 1 is 3. Right now, we are not at that degree of 5. We are currently at a degree of 3. To change it to a degree of 5, we need to get 2 more. But it says all odd. That means I got to change one of these to a 3. I am arbitrarily going to choose the first one. You could have easily put the 3 right here or right here. Please note you couldn't do it on all of them, though, because then the degree would be 9. So the idea, again, 3 and 1 is 5. And an even leading coefficient. So if it wants us to have an even leading coefficient, put a number in front that's even number. How about a 2? Easy peasy. There's my answer. Next problem. Zeros of x equals 0, pi, both even multiplicities, degree of 6, and a fractional leading coefficient. So here we're going to go ahead and get that f of x equals. And a lot of students want to write x minus 0. And I always ask them, why do you want to do that? Even though it's in the definition, x minus 0 is just x. Don't waste your time. Pi is also a 0, x minus pi. Both even multiplicities. So if I put them both at 2, that would work, but the problem is the degree is 6. So you need one of them to have a 2 and the other one to have a 4. You could have done it vice versa, by the way. Could have put x to the 4th and x minus pi squared. That is acceptable, but not a requirement. The degree is 6 now, and a fractional leading coefficient. How about a fraction there? Boom. We're good to go. There's our answer. Number 5. So zeros of x equals 2/5, negative 3/4, any multiplicity, degree of 3, leading coefficients of 200. So zeros of x equals 2 over 5. This one, we're going to start off with f of x is equal to 5x minus 2. This is again from our definition. The idea is this 5 is going to go first, the 2 is going to go next, and because this is a positive, this is a negative. Same concept here. The 4 gets written first, then the x. This is the negative, so we're going to make it a positive, then the 3. The idea is if I plugged in 2 over 5 into this problem, the 5 would cancel, and I'd get 2 minus 2 is 0. If I plugged in negative 3 over 4 here, the 4s would cancel, and you get negative 3 plus 3, which is 0. Easy peasy. Any multiplicity, done. Degree of 3. So if the degree needs to be 3, then one of these needs to be a 2. It can be on either answer. This is actually a question I need to do twice, and the reason why is because you get a different answer for the second half of the question. So we're going to go f of x is equal to 5x minus 2 multiplied by 4x plus 3 squared. These are both our possibilities. When it says a leading coefficient of 200, a lot of students want to put a 200 right in front away. Unfortunately, you can't do that on this question. On all the previous questions, you could have, because these x's all had 1s in front. But here the x's do not. So if I were to actually multiply this guy out, like if I were to do 5x minus 2 times 5x minus 2 times 4x plus 3 and do some FOILing, at some point in time, I'd end up with a 5x times a 5x times a 4x. Because I have a 5x squared, so I get a 5x and a 5x and a 4x. And that means that the current leading coefficient is 5 times 4 is going to be 100. X cubed is the current version of it. But I want a leading coefficient of 200. It's currently 100, so that means I got to throw a big, boom, 2 right there in front. Because if I put a 2 there, then my overall leading coefficient would now have a 2 times 5x times 5x times 4x. And that would give me a 200x cubed. If you wanted to know a way of actually solving this question in terms of like not just doing it in your head, what you could have done is said, hey, my leading coefficient is the letter A, and then we're going to multiply that by 5 times 5 times 4, and that has to equal 200. The 5 and the 5 come from this, and the 4 come from here. However, if you were to write the question this way, you do not put a 2 in front because a different problem is going to show up. Instead, you're going to have A is equal to 5 multiplied by 4 multiplied by 4 because of the A times, sorry. No, I said A equals. A times 5 times 4 times 4 because there's 1 5 here and 2 4s there. And that has to equal 200. And if you do it this way, you get A times 5 times 4 times 4 is 80. And therefore, A on this problem is going to be 200 divided by 80, which is 20 over 8, which is 10 over 4, which is 5 over 2. So these are the two possible correct answers. If you chose to put the square here, the 2 is in front. If you chose to put the square there, you get 5 over 2 in front. Not too bad. Let's do the next set of questions. This one is the other way around. Based upon the above definition, state each zero, the corresponding multiplicity, total degree, and leading coefficient. So it's the same exact thing, but backwards. Here we go. So you're given this guy in your factored form. If you have that factored form, these questions aren't too big a deal. So first we have to write all of our zeros. So we have x is equal to 4 is 0 because it's the opposite of the sign. The multiplicity of that 0 is equal to 3 because the exponent is 3. Likewise, on this one, if I had my x is equal to -2, my multiplicity is equal to 2 because my exponent is a 2. After that, the degree on the problem, always add the multiplicities up. The total degree is 5. And the negative in front is that leading coefficient because we only have 1s there. So the leading coefficient is -1. Let's move on to the next question. Over here, we have now a 0 of x is equal to -1 divided by 5. So it's always going to be that number over that number with a negative. It's the backwards version of the question we were doing earlier. Over here, we have x is equal to -7. The multiplicity of our first one is 2 because of that exponent. The multiplicity here is 1 because of this exponent. Finally, the degree on this problem would be 3 because we have 2 plus 1. Leading coefficient, we have to do a little bit of work to figure out the leading coefficient. We have 2 multiplied by 5, multiplied by 5, multiplied by 1, 2 from there, 5 times 5 from the squared, times 1 there. 2 times 5 times 5 is 50. Let's do another one. Oh, we can't do another one because I didn't make another problem. Mr. Richards. Oh, well. We'll have another one in class then. End behavior, definition. This is pure definition stuff. I did not put any examples right here. I'm just going to go ahead and teach it from another perspective. How do I want to do this? Pausing video. All right, I'm going to keep on. I'm just going to go for it. Here we go. End behavior. So this is our definition. It's a description of what is happening to a value of a polynomial when x is very large in either the positive or negative direction. So the idea is somewhere on a graph, the graph is becoming very, very big or very, very small. So pausing video again. All right, we got Desmos up on the screen. So idea here is if I were to do f of x is equal to, let's do the original function I started off with today. I said 4x squared minus 3x plus 2. Here's my graph, my polynomial. The end behavior is what is happening on the far right-hand side of the graph when x is all the way off to the right or all the way off to the left. When x is all the way over here on the right-hand side, we'd say we're at positive infinity. When x is over here, all the way on the left, we're going to negative infinity. However, I'm not talking about -10 and 10. Like those are not, that's not infinity. I'm talking super duper crazy large to the point where you can't even think anymore. Here's like a 300,000. And just for the sake of doing it, I'm going to go ahead and change my graph really quick. I'm going to change my y, what do I want to do? I'm going to change my x-axis to not be quite so crazy. So maybe a -1,000 up to +1,000. Let's see what happens if I do this. The point is you actually still get a parabola even when you zoom out in a certain way. And as you go to the right, the graph goes up. And as you go to the left, the graph also goes up. So on both sides, the way we are going to word this exactly is we would say as x increases without bound, f of x increases without bound because they are both increasing. As x decreases without bound, f of x increases without bound. As it goes left, the graph goes up. However, this changes depending only on this very first term. These terms don't matter at all. If I go ahead and added another couple of zeros to this guy, the end behavior is the same. The graph doesn't change at all, besides moving up and down, but the end behavior is the same. If I make this 3 and I add some zeros to the 3, you can see the graph moves a little bit, but the end behavior is the same. It still goes up on the left and it goes down on the right. However, in the event that I change this guy to a -4, I don't even change the number, I just change it to a -4, the graph flips upside down. And because it flips upside down, now it's going down on both sides. And we would say as x increases without bound, as it goes to the right, f of x decreases without bound. It goes down. It will also change depending on that biggest exponent. If I simply add in a single x cubed into this question, all of a sudden the graph changes completely. So it doesn't even matter that this is a 3,000 or this is a -4. Now that there's this plus x cubed, there's a bigger degree. That is why we talked about earlier the leading coefficient in the leading term. The leading term determines your end behavior. You can see it's going up on the right here and it's going down on the left. Pausing, continuing again. So the idea here is what these notes are at the bottom of the page. I'm going to zoom out so you can actually see these notes here. But the idea is when x has an even degree and a positive leading coefficient, you will always write this. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to infinity. In calculus, we will use the word limit, and we're going to be using that limit version of writing a little bit later as well. Either way, this graph is going to help us answer all of the questions on the next page for that exact reason. So let's check it out. Ooh, it's that first problem from the beginning of the day. So here we go. We have 8 plus 100x cubed minus 1/2 x to the fourth. We already talked about this one, where this guy right here is our leading term because it has the largest exponent. So that leading term is negative 1/2 x to the fourth. That means you have a negative, even. So your negative coefficient, even exponent. From the page before, a negative exponent with a leading coefficient will always end up looking like this, and you're going to write this entire thing here. So that's what we're going to go ahead and write. We're going to go ahead and say, we're going to write as x approaches infinity, f of x approaches negative infinity. That is to say, as you go right, you go down. So as x increases, y decreases. As x goes up, y goes down. As x decreases, f of x also decreases. This guy goes down on both sides. If you're struggling to remember, sometimes just drawing that little picture can help. Because if you draw that little frowny face there, you can see, hey, on the left it goes down, on the right it goes down. If you wanted to write this in fancy English, there are a lot of different ways to say it. So my favorite way is as x increases without bound, f of x decreases without bound. Let's take apart what these words say. As x increases, increase just means gets bigger. Without bound, a bound is like a boundary. So when you're bound together, it has like a wall or something you cannot cross. So x increases without the wall, without boundary. Then f of x decreases without the boundary, without that wall. So just as x goes up, f of x goes down. We could also say it in the fancy calculus way. The calculus way would be like this. So I'm going to write this in blue because I like this calculus way here for sure. Actually, let's go purple, my favorite. Where'd my purple pen go? I don't know. I had to press it on my purple pen. I guess we're going to have to go blue. All right. So we would say as, we don't have to say the limit. Limit. Oh my gosh, can't read that. Try again. The limit as x approaches infinity. I guess you could actually write out the word infinity. Is negative infinity. You could write negative infinity. But the idea is as x goes to the right, f of x goes down. And you probably see the limit of f of x. By the way, I got ahead of myself, too excited about the problem. You'd say the limit of f of x as x approaches infinity is negative infinity. Just another way of saying it. Let's do the next problem. R of x equals 2, 3x minus 2 squared, x plus 4. So the first thing we gotta do is we gotta figure out that leading term. That leading term is going to be 2 multiplied by 3x multiplied by 3x multiplied by x. It is going to be this guy times this guy, but that guy again times x. The overall result is going to be 2 times 3 times 3. What is that? 18 x cubed. That is a positive odd Positive odd on the notes from the previous page look like this, which means writing it in the way that I'm going to prefer this year: as x goes to infinity, f of x goes to infinity; as x goes to negative infinity, f of x goes to negative infinity. Because as it goes to the right, you go up. As you go to the left, you go down. By the way, if we were doing it in the calculus way, the limit, the fanciest way of all, the limit as x approaches infinity of f of x, oh, actually of r of x, right? Of r of x is negative infinity. That's the fanciest way of writing it. So as x goes to infinity, at r of x, that function we're looking at, goes to negative infinity. Actually, does it go negative? It goes to positive, doesn't it? Whoops. Positive, positive. Yikes, Mr. Richards, you're getting too tired. You know what? And I think that's it. I think I'm going to be calling it quits right there. There's no need to do any more practice. Should be enough of a video lesson. Hopefully that's what somebody was asking for, just a video version of all this. If you have tips or suggestions, please give them. I would love to be able to help even more. Have a great rest of your day. Peace.